Hello students, welcome to physics class. Today we will be doing certain effects of magnetic field. So first of all, we are starting about magnetic field due to a current element. So for this, we take a current carrying element. This is a finite conductor because it is a current carrying element. So we take it as a conductor, and this conductor is finite. It has two endpoints, that is x and y. It starts from x and end at y. So this is a current carrying element, and the current it is carrying is capital I. So within this conductor, we take a small length dl. So this length element we are calling as infinitesimal length element. What is the meaning of infinitesimal? That it is very small. So within this current carrying conductor, we are taking a very small length element, and this small length element we are calling as dl. And due to this small length element, we want to calculate the magnetic field at a distance small r. And since this magnetic field is due to a small length element, so this magnetic field we are calling as dB. And then we can take the small length element and we can add up, and adding the small dB will get the total magnetic field B. So first of all, we are calculating dB, and then we'll move to B. So P is the point where we want to calculate the magnetic field due to the small length element, and theta is the angle between the small length element dl and this displacement vector r. So theta is the angle between dl and r, that is shown in the diagram. So this diagram you can make it very easily. Take a small finite length element, then a current I is flowing through it. Take a small length element dl at a distance r. Take a point P where we want to calculate the magnetic field dB, and the angle between dl and r is theta. So for magnetic field, we know that the most important rule is Biot-Savart's rule, or we call it as Biot-Savart's law. So here we will study what is this Biot-Savart's law. So this Biot-Savart's law is a very important law for the calculation of magnetic field. So let us study what this law is. So this Biot-Savart's law gives a relation between the current and the magnetic field which is produced due to the presence of current. So the magnetic field which is produced due to the current is directly proportional to the current. So according to Biot-Savart's law, dB is directly proportional to I. Also, the magnetic field which is produced is directly proportional to the length element dl, and it is inversely proportional to the square of the distance at which point the magnetic field is calculated. So these are the three relations given by the Biot-Savart's law. Magnetic field is directly proportional to the current, it is directly proportional to the length element which is producing the magnetic field, and it is inversely proportional to the square of the distance at the point where we are calculating the magnetic field. So we can combine these three relations given by Biot-Savart's law. So it is I multiplied dl and multiplied with 1 upon r squared. So these three relations when combined, this give this relation. So there is a proportionality sign you can see, and whenever we remove a proportionality sign, we introduce a constant. So here again we'll introduce a constant, and this constant is mu naught upon 4 pi. Just for a moment, write down this and I'll explain it to you what this is. So dB is equal to mu naught upon 4 pi, proportionality sign is removed, and what is remaining is I dl upon r squared. So here we have written mu naught upon 4 pi as a proportionality constant. So if I want to write down this relation in another form, I can write it down as dB is equal to mu naught upon 4 pi, that is a constant, then I dl cross r. So simply I have taken a cross multiplication of this length element dl with the position vector r. So if I have introduced one new r in the numerator, I have to use one more r in the denominator. So this r is now balanced. So this above equation may be written in this form, that dB is equal to mu naught upon 4 pi I dl cross r upon r cube. And now you can write down the magnitude of the magnetic element. Magnetic field due to small length element is equal to mu naught upon 4 pi. Then there is a cross product which will give us sine theta. So this is I dl sine theta, and r cancels out with this r. So again I can write it down as r square. So this dB is equal to mu naught upon 4 pi I dl sine theta upon r square. This is what we call as the relation of Biot-Savart's law. So this relation, what we get is from the Biot-Savart's law. So this is an important relation and you should always remember this relation. And now if we come to the constant, that mu naught upon 4 pi is a constant. And 4 pi is having some value because pi is 22/7, that is 3.14. So this mu naught, which is the permeability of free space, or you can say the permeability of vacuum, then this mu naught will be written as mu naught is equal to 4 pi into 10 to the power minus 7 Tesla meter upon ampere. So this is a unit for mu naught, and mu naught is a constant which depends. Mu naught is a constant which always has the value of 4 pi into 10 to the power minus 7. So whenever you are using Biot-Savart's law and you are using this relation, then you can simply write down mu naught as this value, which is always a constant because 4 pi is a constant and 10 to the power minus 7. And always use the unit Tesla meter upon ampere. That is the unit for mu naught. And instead of vacuum or instead of free space, if you are using some medium, then you have to use mu, and this mu is the permeability of that material. Similarly, as in the electric field, we were using epsilon naught, that was the permittivity of the material, and here similarly on the same accounts we are using mu naught, which is the permeability of free space. So epsilon naught shows the permittivity of free space, mu naught shows the permeability of free space. Similarly, epsilon shows the permittivity of a material and mu shows the permeability of a material. So this epsilon naught is having a magnetic counterpart as mu naught, and epsilon is having a magnetic counterpart as mu. So now it will be much easier for you to remember. And from this relation, you can also conclude that its magnetic field is having very much similarities to the electric field. And to calculate the electric field, we use Coulomb's law, and to calculate the magnetic field, we use Biot-Savart's law. So there is a similarity between the Coulomb's law and the Biot-Savart's law. So if you want to look into the similarities between these two laws, on one hand I have written Biot-Savart's law and on the other hand I have written Coulomb's law. So let us find the similarities between these two laws. First is that both these laws are long range. That is the magnetic field which is produced or the electric field which is produced, both are long range. So that is the first similarity. If you come to the second similarity, then it is that both of them follows the law of superposition or the principle of superposition. So both follows superposition principle. And what is the superposition principle? That the total magnetic field or the total electric field, if you calculate individually for the small elements, then the total of the magnetic field either or the electric field is the vector sum of all those individual small components. So that is superposition principle, and this principle of vector addition is followed by magnetic field as well as electric field. So that is the second similarity. And the third similarity between these three is that both are linear in source. What does it mean? That if you are having the electric field, that is due to electric charge, and if you are having a magnetic field, then it is due to a current carrying element. So these three are the similarities, and if you go to the differences between these two fields, then the first difference between these two fields is the electric field is produced by a scalar source, which is an electric charge, but the magnetic field is produced by vector source, that is any current carrying element. The direction of the electric field, that is the electrostatic field, is along the displacement vector, which we call as R. So the direction of the electric field is along the displacement vector R, which is joining the source and the field point. It is the direction of magnetic field B. It is perpendicular to the plane containing the displacement vector R and the current element IDL. So because it is perpendicular to these two, and here it is along the joining source and the field point. Third difference between these two fields, that the electric field, that is the electrostatic field, it does not depend on any angle theta, whereas our magnetic field B, it depends on angle theta, because we have I dl cross r from the Biot-Savart's law, and that dl cross r, that cross product always gives us a sine theta. So due to this cross product dependence, there is a theta dependent of the magnetic field, but electric field does not depend on angle theta, but the magnetic field depends on angle theta. So our electric field does not depend on angle theta, but the magnetic field B depends on angle theta. Now, fourth difference between the electric field and magnetic field is that for the electrostatic field or the electric field, we use epsilon naught for the free space, that is the permittivity of the free space, whereas for the magnetic field, we use mu naught, that is the permeability of the free space, and there is a connection between these two constant quantities, this epsilon naught and mu naught. If you want to find out the relation, you just multiply it with 4 pi and again divide it with 4 pi. So that is the same quantity, epsilon naught mu naught. We have multiplied and divided with 4 pi. So 1 upon 4 pi epsilon naught we write down as 9 into 10 to the power 9. So this is equal to 1 upon 9 into 10 to the power 9. And mu naught is equal to 4 pi into 10 to the power minus 7. So mu naught upon 4 pi will be having the value of 10 to the power minus 7. So if you calculate this value, you get this as this is equal to 1 upon, if you take the 7 down, then 9 plus 7 is 16. So this is the square of 3 into 10 to the power 8 whole square, because this will give you 9 and this will give you 16. And we know that 3 into 10 to the power 8 is the velocity of light, so which we represent as c, that is the velocity of light or the speed of light if you take only the magnitude into account. So this is equal to 1 upon c square. So we got a relation that mu naught epsilon naught is equal to 1 upon c square. That is the relation between the two constants used in the electrostatic field and the magnetic field. So this is the relation mu naught epsilon naught is equal to 1 upon c square. Next we calculated is the magnetic field due to a current carrying loop. So in this question, we want to calculate the magnetic field due to a current carrying loop. So we take a current carrying loop which is circular in shape, and the radius of this loop is capital R, the center is O, and the current which is flowing through the loop is capital I, and we have taken the axis such that we have taken the origin at the center of the circular loop. Here we have axis X, Y and Z. So these are the three axes of the coordinate system. So at a distance x from the center, we take a point P. So at this point, we want to calculate the magnetic field due to this small current carrying element. So we will divide the circular loop into small current element, that is the length element dl. So we calculate, first we will calculate the magnetic field due to the small length element, and then we will add up all these so we can get the total magnetic field. So this is our circular loop, and this loop is carrying the current in the YZ plane, as you can see. So this is the YZ plane of the circular loop where it is carrying the current. And if you want to calculate the magnitude of the magnetic field at any point P, which is at a distance x from the center of the circular loop. So we can direct away use the Biot-Savart's law. So just write down the formula for the Biot-Savart's law. dB is equal to mu naught upon 4 pi I dl cross r upon r cube. This is the formula for Biot-Savart's law. So whenever you are calculating due to any small current carrying element, that is the amount of magnetic field which is due to this current carrying element, you can direct away write down this Biot-Savart's law. Now first of all, we will calculate the value of the small r. So here you can see this triangle. This is from the distance of this point P from the current carrying element is small r, because this is dl, and here we want to calculate dB. So that distance is small r. So here you can see a triangle, and here you can see it is of 90 degrees. So in this we can simply use the Pythagoras theorem to calculate value of this r. So this is r square is equal to capital R square plus small x square. So we can easily write down r is equal to x square plus capital R square. And here if you look at the small length element dl, it is always perpendicular to this r. Either you can choose this point, or you can take this small length element, or you can take any small length element. It is always perpendicular to this r. So whenever you calculate this dl cross r, which is in the Biot-Savart's formula, so dl cross r means dl r sine theta, and theta is 90 degree always. So sine 90 degree will be 1. So this is equal to r dl. So these two substitutions we can do into this Biot-Savart's law. So substituting these two quantities, this and this, if we substitute in the Biot-Savart's law, what we get? We get dB is equal to mu naught upon 4 pi I dl r upon r cube. So this 1 r cancels out. So this is equal to mu naught I dl upon 4 pi r square, and again substitute the value of r. So you will have this as mu naught I dl upon 4 pi, and this is x square plus r square. So this is the form our Biot-Savart's law has reduced to. So the direction of this magnetic field dB will be in the perpendicular to the plane formed by dl and r. So if you see that the plane formed by dl and r, this is the plane you can see. So this will be perpendicular to this plane. So this will be the direction of dB. See, this is the plane which is formed by dl and r. So this is the plane, and if you have to take the perpendicular to this plane, this will be this dB. So this dB is the direction of perpendicular plane of dl and r. So we can take the components if it is at angle theta with compared to the x-axis. So you can take a perpendicular component, that is a normal component, and you can take a horizontal component, which is a parallel component. So if you calculate for these small length element dl, then if you sum out all the perpendicular component, they will cancel out, because due to this dl, it is perpendicular to this plane in this direction. Similarly, if you take this dl, then dB will be in the downward direction. So if you take sum of all these perpendicular sums, so all the perpendicular components, when summed, they cancel out. So we will have only parallel component, and this parallel component is along the x direction. So we can write down this parallel component as the component in x direction. So this will be dB cos theta, and this will be dB cos theta, and this will be dB sin theta. So what we have is dB cos theta. And if you want to calculate this value of cos theta, it comes out to be, because if this angle is theta, then this would also be theta. So if you want to calculate, because if this angle is theta, then this angle would also be theta. So if you want to calculate the value of cos theta, then this is r upon under root r square plus x square. So what we have, the Biot-Savart's law, we have only the x component. This is equal to mu naught upon 4 pi I dl. This is the value of dB we have put. Now we have to write down this dB value will be having x square plus r square. Then dbx is equal to dB cos theta. So this is the value of dB. Then we have to put the value of cos theta. So cos theta is equal to under root r upon under root r square plus x square. So if you sum out all these terms, what you get as a resultant is dbx, that is a parallel component of the magnetic field, is equal to mu naught upon 4 pi I dl r upon, this is r square plus x square to the power 1, and this is r square plus x square to the power half. So if you add these two, you will have r square plus x square to the power 3 by 2, that is 1 plus half is 3 by 2. So this is the magnetic field due to the small length component dl. Now if you want to calculate the total magnetic field, then you have to add up these small components following the principle of superposition. So let us see what will be the resultant total magnetic field. So total magnetic field B will be along x direction because this is all the horizontal component that will be taken into account. So if you sum up all these, you will have mu naught I r upon 4 pi r square plus x square to the power 3 by 2, and this will be integration over dl. So if you take the integration of all these small length element dl, that means we are moving through the circumference of the circular loop. So if you take the integration of total dl, then the circumference of a circle will be equal to 2 pi r. So the value of this integration dl is equal to 2 pi r. So on substituting the value, what we get is Px is equal to mu naught upon 4 pi I r square plus x square to the power 3 by 2, and this is 2 pi r. So this cancels out, and here we have 2. So this is equal to mu naught I r square upon 2 r square plus x square to the power 3 by 2. And the direction is I cap. So this is the total magnetic field which is created due to a current carrying circular loop. So always remember this formula. So always remember this formula, because this formula will be useful for your 12th class or for all of the competitive exams, as well as solving the numericals. All the numericals, if you're using for a circular loop, then this formula should be on your tips, as well as if you're working in a physics lab, then you have to calculate it at any point on the axis of the circular loop, then you have to use the same formula. So at any point P, which is at a distance x from the center of the loop, then the magnetic field at that point is mu naught I r square upon 2 r square plus x square to the power 3 by 2, and the direction is along the axis. That formula should always be on your tips. And in a particular case, if you want to calculate the magnetic field at the center of this loop, so let us quickly go to the diagram we made. So this total magnetic field we have calculated at point P due to this circular loop. So this is the formula we get, and if we shift this point P at the center of this loop, that means this distance x becomes 0, because x is the distance from the center to point P. If you shift this point P to the center O, then the value of x will become 0, right? So then you can easily get the value of magnetic field at the center of the loop. So that is a special case. So we'll write down when the value of x is 0, then we can calculate the magnetic field at the center of the circular loop. So that is a special case. So magnetic field at the center of the circular loop. So it implies the value of x is equal to 0. So if the value of x is equal to 0, just put x equals to 0 in this formula. So this is only r squared to the power 3 by 2. So this power 2 cancels out. So we have here r cube, and here we are having r squared. So this r squared, 2 power cancels out here. So we will have only 1 r here. So the formula will reduce to b is equal to mu naught I, r square is already cancelled. So this is 2r and the direction is I cap. So we have just simply put x into this formula, and simply by putting x equals to 0, you can always calculate the magnetic field at the center of the circular loop. It is that easy to get, but it is always right. So just remember this thing, that putting x equals to 0 will give you this value. So whenever you want to calculate or whenever you want to find out the direction of magnetic field lines, then you have to use right hand thumb rule. What this rule is, that if the direction of flow of current is known to you, say we have taken a circular loop here, which you can see in green color, and in this green color circular loop, if you can see this arrow, these are the two arrows which shows the direction of flow of current. So the current is flowing in this direction, in an anti-clockwise direction. So just use your right hand, and if you fold your fingers in the direction of flow of current, that means if you fold your fingers like this as shown in this diagram, then your thumb will be moving in the upwards direction. So if this shows, the folded fingers shows the direction of electric current, then your upward thumb will show the direction of magnetic field lines. So here you can see the direction of magnetic field lines. So here it is straight in the middle, then it bends like this. So this is like, so this will be how you can draw the magnetic field lines. So whenever you want to know the direction of magnetic field lines, simply use the right hand thumb rule and you will always guess it at right. So always remember that right hand screw rule you have to use for the magnetic field, and for the magnetic field lines you have to use the right hand thumb rule. Now let's study about Ampere's law, because we have done up with the Biot-Savart's law, and the next important law is magnetic field is, or magnetism is, Ampere's law. And Ampere's law is the magnetic counterpart of what we studied as a Gauss law. So if you've gone through the lectures on electrostatic and current electricity, then you might have experienced how easy it is to do the calculation if you are using any static charges or a continuous charge distribution. Then you can easily apply the Gauss law for the electrostatic field. Similarly, for the magnetic field, which is a magnetic counterpart of the Gauss law, is that important is the Ampere's law, and this is also known as the Ampere circuital law. So we'll study what this Ampere law is. So in order to study the Ampere's law, we take a open surface or a boundary through which the current is passing. So let us say we take a circular boundary, and through this boundary or through this surface, which is an open surface, the current is passing. And here somewhere, so this is the current. So this is a circular loop through which the current I is flowing. And if we take any of the small length element dl, and we calculate the magnetic field, then we say that the tangential component of this magnetic field is the perpendicular. So we can add all these small components as we have just done. So we can add these small components and we can get the total magnetic field. So the total magnetic field will be due to through this closed surface. So we can do B dot dl. So that will be the total magnetic field. So the Ampere's law says that the total magnetic field through this closed surface is equal to mu naught times the current I. You can write this down as small I, or if you wanted to make it capital I, the current you want to make it capital I, then you can also say that if the current through this loop is say capital I, then you can make it capital I here. So B dot dl is equal to mu naught I. So this is the statement for the Ampere's law, that the total magnetic field through a closed surface is equal to mu naught times the current flowing through it. So that is what is the statement of Ampere's law. And this Ampere's law also follows right hand rule. What is that rule? That if the curved finger shows the direction of the magnetic field, then the thumb represents the direction of flow of current. So the Ampere's law also follows right hand rule. And second thing is that Ampere's law is valid whenever there is a symmetry. So let us say, to consider the symmetry condition, we can say there is a straight wire, long wire, which is carrying the current I. And if you want to calculate at any distance r, if you want to calculate the magnetic field, then you can draw a circular loop around it and say this distance is small r. Then you can calculate, you can use Ampere's law, B dot dl is equal to mu naught I. So here B is the magnetic field, and dl if you take for whole of this circular loop, then it is again 2 pi r. For the circular loop, r is the radius because we are considering any point at a distance small r from this current carrying wire. So B into 2 pi r is equal to mu naught I, or from here if you calculate the value of B, it is mu naught I upon 2 pi r. So since this wire is having a circular symmetry, so we have simply applied the Ampere's law and we get the answer that B is equal to mu naught I upon 2 pi r for a current carrying wire. So this wire, if you consider it has a cylindrical symmetry, so you can easily draw a circular loop. And if you want to know the direction, then just fold your direction of magnetic field, then your thumb should be pointing upward because this current is in the upward direction. So if your thumb is pointing in the upward direction, then your fingers are folded like this. So this will be the direction of magnetic field. So this shows the direction of magnetic field. So again, you can employ your right hand rule here. So if these are your folded fingers, then these shows the direction of magnetic field, and your thumb is pointing upwards in the direction of the current flow. So simply you can apply right hand rule here. So these are the two important things. This is the Ampere's law. It follows the right hand rule, and whenever you are applying it, it should have a symmetry. On the grounds we are considering the Gauss law. Similarly, we have to consider the Ampere's law. Then there are two very important applications of this Ampere's law. One is the solenoid and another is the toroid. So these are two very interesting things, and I personally like this very well. So let us go to these two interesting things. First solenoid and then toroid. So here in this diagram I have shown a solenoid. A solenoid is basically a long wire and it is wound in the form of helix. As you can see, that it is wound in the form of a helix, and these wires are closely spaced. So the net magnetic field is the sum, that is a vector sum of field due to all turns. So here you can see that this is a wire and it is in the form of helix. So these are different turns of the solenoid. So for the diagram, we have shown a finite solenoid and we have shown the magnetic field lines for this finite solenoid. And the solenoid is used to generate magnetic field, because if a long wire is wound and the current is flown through this, then it will create a magnetic field around us. So this is basically a long wire and which is wounded in the form of a helix. So here we have shown the magnetic field lines that you can see in the diagram. So if you go into these small loops, then if you see this loops, the current is flowing in the anti-clockwise direction, and in the nearby loop it is also in the anti-clockwise direction. So here it is going upward, for the second loop it is coming downward. So these two nearby loops cancels each other. So what we see that these circular loops shows that the field between two neighboring turns vanishes. Similarly here it is in the opposite direction, so it vanishes, here it vanishes, here it vanishes. And similarly here between these two turns it is in the opposite direction, so between these two neighboring turns the magnetic field vanishes. So for these outer all these turns the magnetic field vanishes. So the magnetic field will only be in the interior point of the solenoid we have shown. So let us take any interior point. So let us say that P is any of the interior point inside the solenoid. This is any point P which is situated inside the solenoid. I hope you could see this point P which is inside the solenoid. So here the magnetic field is quite strong inside the solenoid, and at the interior midpoint P this magnetic field is uniform, it is strong, and along the axis of the solenoid. This is the axis of the solenoid, so the magnetic field is along the axis of the solenoid. And for any point outside, say Q is any outer point, so any point outside the solenoid, the field is very weak and along the axis of the solenoid. So the field outside the solenoid approaches 0. And the field inside the solenoid is everywhere parallel to the axis. So since it is having a symmetry, so we can draw any of the Amperian loop. So let us draw an Amperian loop for this solenoid. So here I have shown a solenoid. Whatever you see in a blue color is a solenoid. So if you see this loop in the upper parts of the solenoid, then it is in the counterclockwise direction. So if you use the right hand rule and you fold your fingers in the counterclockwise direction, then your thumb is pointing outward. So that means the current is flowing in the outward direction. And for the outward direction, we always use a dot to represent. So here in the upper part, I have used a dot which shows the direction of the flow of the current. And if you go to the lower part loop, then it is in the clockwise direction. So again, if you use the right hand thumb rule and you fold your fingers in the clockwise direction, then your thumb is always pointing downward. So the current is flowing in the downward direction. So I have shown it with the cross, because cross always points the downward direction, that is into the plane of this sheet. So that shows the direction of current. So this is solenoid, whole of the solenoid. That is the wire bounded, current carrying wire bounded in the helical forms, and this shows the direction of current. And with the green lines I have shown the direction of magnetic field lines. So to take the amperial symmetry, we have drawn a rectangular loop here, this loop A, B, C, D. So this arm AB is inside the solenoid and CD is outside the solenoid. So we want to calculate the magnetic field by making this amperial loop. So if you employ the Ampere's law, that B dot dl is equal to mu naught I. So if you come to this arm CD, here the current flowing is 0. So along CD the field is 0. Because there is no current. And if you come to these vertical arms, this is BC and AD. So if you come to BC and AD, that are the transverse sections, then you see this B dot dl is equal to B dl cos theta. Then the angle between them is 0 because it is in the same direction. Now the only thing left is that is along CD. Along CD, if you do B dot dl is equal to mu naught I. So here we have shown the point P inside the solenoid and the rectangular loop. So we will do one by one. Along CD we got it as 0 because there is no current which is flowing. So since I is 0, so from the Ampere circuit law we get the magnetic field as 0. If we take these two vertical components, this AD and BC, then here you see that is the direction of magnetic field lines. And you can also draw here the right hand rule. So this will, if this is the direction of flow of current, as you can see that this is the direction of flow of current, and these are the magnetic field lines, as you can see. So for these two components, the angle between this B and DL is again 90 degree, and cos 90 will give us 0. For all these two vertical components, it becomes 0. So for CD is equal to 0, similarly AD and BC is equal to 0. So the only part that is remaining is along AB, that is in the interior of the solenoid. So for here we have used simply Ampere circuit law that B dot dl is equal to mu naught I. Here this dl, the length of this is h. So we have put this dl as at B dot h is equal to mu naught I. Now current I is flowing through the small number here we have use this turns. So n is a number of turns per unit length. So if this length we have taken as h, so we'll multiply this number per unit length with the length. So that will be the total number, and the I current is flowing through each of them. So this is mu naught I and h. So this h cancels out, which is the value of dl. So we have B is equal to mu naught and I. So the magnetic field, which is only in the interior of the solenoid, which is equal to mu naught and I. Here n is the number of turns per unit length. So if the total turns are n and you divide it with the length, then you will have the number of turns per unit length as n. So if you are given with the total turns, then you have to take it as B is equal to mu naught n upon L into I. But if it is given with the number of turns per unit length, then you will simply use B is equal to mu naught n I. So similarly, we have done very simply solve this for solenoid using the Ampere circuit law. So this is just an application of how we use solenoid to generate magnetic field, and we can easily calculate the magnetic field. The second application is the toroid. Here you can see a very simple diagram of the toroid, the solenoid and toroid. This toroid is also used to generate the magnetic field similar to the solenoid. The only difference between solenoid and toroid is that here we join both of the ends of the solenoid. If you join both ends of the solenoid and make it in a circular shape, then we call it as a toroid. So a toroid is a hollow circular ring on which a large number of turns of wire are closely wound. So here you can see that we are having a large number of closely wound wires on this circular ring. So this we call as toroid. Here there is a wire which through it is entering, then it is closely wound, and that is the other end. So the current which is flowing through the wire is capital I. And here we have taken 2 points. Point P is inside the toroid somewhere and point Q is outside the toroid. So if you go to the inside of the toroid, here you can see that there is no current present. And if you use the Ampere circuit law, B dot dl is equal to mu naught I, then I is 0 here inside. So there is no current, so the magnetic field will be 0. Similarly, on the outside point Q, if you see there, here also there is no current. So since there is no current present, so the magnetic field is 0 using the Ampere circuit law. Now if we take any point here somewhere inside this toroid here, say this point is B. So here we take a point B which is situated, here you can see the point B where it is situated within the toroid. So here we are having the current, so the magnetic field will be present, but it will be constant as magnitudes, because everywhere if you move around the circular loop, then this magnetic field will be same. So here we can apply Ampere circuit law. So in order to apply the Ampere circuit law inside this toroid, we have to take a cross section. So let us draw a cross section of this toroid. So here we have drawn a cross section of the toroid and it is zoomed. So whatever you see as solid lines shows the toroid. So these are the 2 lines corresponding to this toroid. And whatever you see dotted 1, 2, 3, these are the 3 Amperian loops. So 1, 2, 3 are the 3 Amperian loops. So Amperian loop 1 is inside the toroid. That is in the Amperian loop 1 is the interior of the toroid, that is here somewhere. And this Amperian loop 2 is within the toroid, that is this here somewhere. And the Amperian loop 3 is just outside the toroid, somewhere outside here. So now we can calculate for these 3 reasons very easily, because let us say that the magnetic field along loop 1, you can see this loop 1 that is in the interior of the toroid. So let us say that the magnetic field along loop 1 is B1. So for B1, for Amperian loop 1, V1 into 2 pi R1, because dl here it is a circle with the radius of R1. So B1 into 2 pi R1 is equal to mu naught I. And since in the interior of the toroid I is 0, so it implies B1 is equal to 0. So for the Amperian loop in the interior of the toroid, the magnetic field is 0. So the magnetic field at point P, which is in the interior, here the magnetic field is 0, that we have derived. Now we come to the outer loop, that is in the exterior of the toroid. So for American loop 3, so for Amperian loop 3, B3 into 2 pi R3 is equal to mu naught I. So if you see here in the exterior that if you see the cross section, then the current coming out of the plane of the paper, as you can see, that is the current coming out of the plane of the paper. It is cancelled with the current that is going down into the plane of paper. So these two cancels out each other because these are in the opposite direction. So these equals each other for a loop. If you see, then here you can see that whatever is coming outward is similar to going inward. So these two cancels each other. Then the total current I is equal to 0. So since I is equal to 0, the magnetic field B3 is 0. And why I is 0? Because that is the reason that the current coming out of the plane is cancelled by the current going into it. So that is the reason for the third loop, that is in the exterior, we have the magnetic field as 0. Now the only Amperian loop we are left with is Amperian loop 2. So let us move to Amperian loop 2. We can write down B into 2 pi R2. Here we have radius taken as 2 pi R2 is equal to mu naught I. And since if we take the total number of turns as capital N, so the current flowing into each turn will be N into I. So B into 2 pi R is equal to mu naught Ni. And since this point is in the toroid itself, so whatever So whatever is the radius of the toroid will be the radius R2. So we can replace this R2 with R. So what we get is B into 2 pi R is equal to mu naught Ni, or B is equal to mu naught Ni upon 2 pi R. And if this number n we take as n upon 2 pi R, that is the total numbers divided with 2 pi R, that is small n, then we can also write this formula as B is equal to mu naught Ni, which is similar to the magnetic field as we have calculated for the solenoid. So B is equal to mu naught Ni, which is in the toroid itself. So let us firstly conclude what we have done. So this is a toroid. We have taken a cross section of the toroid. So here we can see in the interior of the toroid, here the point P we have taken. So for this point P you can say, there is no electric current, so there is the magnetic field is 0. If you come to the outer side, then whatever is entering is leaving. So you can see that here this two currents cancels out each other, outward and inward to the plane of the paper. They cancels out each other, and so the exterior of the toroid, the current is 0, so the magnetic field is 0. And if you go in the toroid itself, you see that between these two solid lines we are having the Amperian loop 2. So here we are somewhere at this point P. So here you can take P into 2 pi R is equal to mu naught Ni, because n is the number of loops. So we have the similar formula for a toroid. It comes out to be B is equal to mu naught Ni. So just easy to remember that a magnetic field for solenoid or toroid is the same, B is equal to mu naught Ni. But for solenoid, small n is the number of turns per unit length, that is capital N upon L. And for toroid, the small n is capital N upon 2 pi R, because toroid is in a circular form. So both the formulas are same, and these are the very easy applications, and you can solve a number of numericals using it. So that's all for today. If you like this lecture, then like and share and subscribe to our channel Physics Class so that you can receive notifications for more such interesting lectures. Till then, keep going, keep studying, and keep rocking. Thank you.